Good afternoon, those of you who are on conference time. That's Melbourne time, Australian Eastern time. And good evening to those of you from California, which is the land whence comes Paco Nathan, known in the industry as a player slash coach with core expertise in data science, natural language processing, and cloud computing. About 40 years of tech industry experience ranging from Bell Labs to early stage startups. He has too many accolades to list completely, but there are some highlights. He's the lead committer of PyTex Rank and KG Lab, which he will be talking about today. And formerly, he was the director of community evangelism for Databricks and Apache Spark. If you want to know more about him, you can find out at derwent.ai/Paco. And his talk is about how graphs are amazing. There's the emerging graph ML work in deep learning. There's the rise of knowledge graphs in industry, powerful graph algorithms, huge graph databases, interactive graph visualizations, and so on. But it seems like a bit daunting. Paco's talk is about how you don't really need to have like special platforms and very specialized knowledge. You can start on graph-based technologies using just Python, KGLab, and many of the other Python technologies that you already know and love. Please give a virtual hand of applause and show your love to Paco Nathan and Graph Data Science.
Thank you very kindly. Thank you, Javier. I appreciate it. And I'm grateful to get to present here today. The slides are online. I probably err on the side of having way too many links in my slide decks. So there's the link here, and it should be in the chat as well, and I'll be on chat afterwards. But if you want to check through the slides, there's a lot of links out to primary sources and repos and articles and whatnot. So this is about graph data science. And just briefly about me, I've been doing this for a few years, but I had some interest in neural networks a long, long time ago. I got involved in machine learning back in the 80s, and then nobody cared, so I did a lot of work in network engineering. I ended up being a guinea pig for something new that was getting launched that I found out later was named AWS, and I ended up leading one of the first large Hadoop instances ever running in the cloud. And then from there into Spark and working with Jupyter and Ray and some other projects. So this talk is really about understanding how to work with graphs, because there's so much open source that's available. So I want to lead you through a brief story. Imagine here, this is a village. Let's say it's a medieval village somewhere in the Black Forest. And it's beautiful, of course. And if you want to look at it in terms of a map, there's a road running through and a stream running by, and some different cottages and businesses and whatnot. So let's talk about who's there in the village. We've got Pat. Pat runs the pub. Pat has a couple of friends, Hannah and Thomas. Now Hannah works the fields and produces grain, and she's got a friend, Aiden. And then Thomas raises poultry, produces eggs. And Thomas has a friend named Brenda. Now, if we go back to Aiden works the mill and takes the grain from Hannah and produces flour. Aiden has a friend, Chris. And then Brenda, she takes the grain from Hannah and she works the brewery, produces beer. And she's got a friend named Kim. And then there's Chris. Chris runs the bakery, produces bread. Now, Chris is taking products from Aiden, the flour, and eggs from Thomas, and selling the bread back to Pat at the pub. So they've got some nice bakery goods. And then Kim runs the recycler. She buys organic wastes from Thomas and Chris and all, and then she produces fertilizer that goes back. Hannah buys that to use in the fields. And the point I want to make is that with 7 nodes here, 7 people in a small medieval village, we already have a definition of what we would call a circular economy. We have something that's sustainable, and we have this producer-consumer view of what they're doing, what their activities are. We have a friend graph. We also have this product graph, if you will, the flows of products going through this workflow. And so this is a graph, and this is the way you think about how a complex, intertwined system operates. Now, if we were to take that very same data and put it into a relational database and do the proper things in terms of normalization, it would look most likely very much like this. In some ways, you have to take uh, and dismember all those relationships and connections that you had and put them into tables. And you can kind of see this here. Can you understand who's really producing the most important goods by looking at these numbers? That's hard. However, if you come back into a network view, you might get a better sense of it. So when you do have complex contexts, network views bring the data and the connections within the data closer to the people who can make sense of it. And this is predicated on a few things. One is acknowledging the complexity of the kind of use case you're working with, the context, and then being able to understand, can we identify emergent patterns within these connections? And from there, be able to make informed decisions. So think about patterns. Whenever you're working with graphs, think about patterns, or vice versa. When you're seeing complex patterns, perhaps graphs are indicated. Now, Hannah is relatively new in this village, but she'd like to expand her business. So one question naturally she could ask is, she's noticed that one of her customers, Brenda, buys a lot of grain. Who are the other villagers who might be similar to Brenda? Can we do some lookalike analysis? And if you go across the graph and do some analysis there, you find that, well, Chris also sells product to Pat, and he sells waste to Kim. Maybe the bakery could make good use of unmilled grain. Maybe they could produce malt or something. Hannah is also interested in sponsoring a co-marketing campaign here in her medieval village to help drive demand. So helping out her customers to reach more of their customers. Who are the customers of Hannah's grain business? As it turns out, Chris, Pat, and Kim are each a minimum of 2 hops away, and we can see this from graph analysis. Now, just suppose you had some tech billionaire, some Elon Musk type, who uses time travel to relocate back to a medieval village in the Black Forest, like you do. Which businesses are the most influential if they were to, perhaps try to have an acquisition target? It turns out that if you look at this medieval village and the business going on there, Hannah and Chris are the ones that they're really the most central figures. And in fact, if you run graph algorithms on this exact data, you find out that Hannah leads the ranking in terms of using a betweenness centrality measure. Now, also think about what happens if somebody new comes in. Mika is an old friend of Kim. She's just moved to the village. She has a delicious recipe for chicken sausage. That's going to require some poultry and some grain. So, think about, how would you position Mika in here? How would she be connected? Naturally, of course, she could sell sausages off to the pub, so Pat would be interested in buying those. So this type of approach is very minimal to bringing in new data acquisition, and data integration, I think is probably a better way to put that. I want to bring this back to something that isn't really about technology. Let's talk about pedagogy. Let's talk about learning and teaching. Susan Ambrose has a great book called How Learning Works. It's one of the typical kinds of textbooks in field of pedagogy. When people look at the cognitive psychology of how individuals learn, how people proceed from being a novice into gaining more and more expertise in a given field, well, we can talk about that. At first, when someone's a novice, they tend to learn relatively superficial mental structures, disconnected sets of simple facts. And of course, when we're building tests, we query for that. And then as people become more advanced in a practice, they start learning how to string together different facts, and they can make associations. These tend to be represented as far as like linear kinds of sequences of cognitive structure. But then when people become much more practitioners, they tend to think in terms of something quite like decision trees. And at this stage, people can really get into, a lot more decisions and formulating plans and whatnot. But when people begin to show expertise in a given field, one of the first things that they almost always do is they learn where to break the rules. Those decision trees of rules, they know which parts of those they can rely on and which parts perhaps are questionable. And so when you start to look at the cognitive structure for how experts work, they organize what they have learned in terms of graphs. And this is what the cog sci people say, AI notwithstanding. The experts look for emerging patterns when they try to make sense. Now, I could go into much more detail too. I'm going to skip over this part. If you've ever heard the rather unfortunate use in the United States of the unknown unknowns back 20 years ago, it derived from a gentleman at IBM named Dave Snowden, who had the Cynefin framework, talking about how leaders make decisions. And in this, there's a sense of simple context where you follow best practices. You have facts that are established, you follow the rules, done and done. But then when you get confronted with a more complicated kind of problem, you typically have to bring in some experts and they do some analysis, and that leads to decision making about trade offs. But then you get into a complex place. And this is where you reach the infamous unknown unknowns. Determining cause and effect just doesn't work. So instead, you have to look for emergent patterns. And again, we see this over and over again in business in terms of how do we approach management. When you hit complex business problems, you're looking at emergent patterns, you're dealing with uncertainty. And for global business today, this is where we're at. So I just want to make the sense that relational data and data warehouses are really great if you're operating at the level of, say, a novice or an advanced beginner. When you proceed into more of the complicated, competent practitioner type systems, yeah, okay, maybe some of the analytic warehouse approaches, that's good. That's where data science tends to live. But when you get into the expert parts of this, you need to be leveraging graphs. And we know this even before the technology begins to get applied. Uh, and I will say that, if you look at the literature, Gartner, up until 2020, Gartner Research was saying that, well, I'm not really so sure about graphs. They did an abrupt about face early in 2021, and they are now saying, no, actually, even though graph analytics is at 10% penetration in industry, today they're projecting that by 2025, graph technologies will be used by 80% of data and analytics. And currently, over half the inquiries that they get from enterprise about AI are about graph technology. Right here, this bottom line is really good. The very thing that's happening in the background when you're running a SQL query or when you're using an Excel spreadsheet, the very thing that's happening is it's a graph that's executing. And the metadata and the business rules that are being applied are through a graph, but those are hidden behind the scenes to make them look simple. Now, the problem is, as we learned from Cynefin, if you take a very complex kind of problem and try to oversimplify it, bad things happen. We saw that in the United States, certainly where the unknown unknowns came into play. So, this point about a village and about graph thinking, we can embellish this a bit more. I want to shout out to some very good friends and colleagues, Jürgen Mueller at BASF. There's an article called Graph Thinking that goes into much more detail about this. And I'll give Jürgen credit. He and I developed this whole village thing together. We've been using it to help train executives in graph thinking. There's also a recent podcast with my friends Ben Lorica and Jen Webb talking about this kind of surge in interest in graphs. And along with it, also, I'll point out a really good article from last year by Cassie Kozakov about what is ambiguity aversion. Because I'll say this, one of the points that Jürgen Mueller and others out in industry make about graphs in industry is that when you propose using a graph for a problem, typically about half the people in the room who are domain experts, they'll get it. They'll jump right into it. It's how they think about their problem, whether they're working in logistics or market intelligence or some sort of, business process. But the other half of the people run screaming the opposite direction. And there's a reason for this out of behavioral economics. It's something called ambiguity aversion. And we could go into more detail, but Cassie has done a really fantastic article about that. So, moving right along, there's something called graph theory, especially algebraic graph theory, which says that if we do have complex data organized as a graph, there's nodes and edges and properties and all that, we can take and simplify this and turn it into, on the one hand, a vector, really simple case, or a matrix. That's a very common case in algebraic graph theory, or a tensor if you want to capture more of the nuances of the graph. This is a very mathematical kind of approach to working with graphs, and it tends to move everything into a numeric space so that we can do number crunching with things like GPUs, which is very useful. But I want to make the point, sometimes we must use both the symbolic and the numeric. The numeric is great if you're doing deep learning or graph algorithms or visualization. But if you're auditing for compliance, you're working with natural language applications, you're doing human in the loop, if there's rules regarding domain expertise that have to be merged in, or if there's needs to explain what your models are doing, you're going to be in the symbolic space. So you need to be able to have transforms back and forth between the numeric and the symbolic. And we provide this in an open source sense. It's very similar to, say, what label encoding does in scikit-learn, or, of course, embedding in PyTorch and other types of deep learning frameworks. And in general, this idea of going back and forth between numeric and symbolic, there are analogies. I like to think of it as something called thinking sparse and dense, with all apologies to the author of Thinking Fast and Slow. But the idea is that when you're working with data and workflows, it's really crucial when you're thinking about how to leverage the hardware. At some stages, you must work in a sparse sense, and these are typically bandwidth limited. Uh, and even parts of deep learning, when you're calculating a loss function, it's typically sparse like this, and it's bandwidth limited. Data preparation is like that. But then there are other times we need to crunch on a very dense piece of data that can be packed into a GPU, like the convolution layers in deep learning. That's compute limited. And if you want to go into more detail on this, there's a recent report Dean Wampler and I just did for NVIDIA, working with the open source leads, tech leads at NVIDIA. It's called Hardware is Greater Than Software, Greater Than Process. And I'm throwing this out here as a sense of graph data science. How can we leverage graphs? How can we leverage the dimensionality within graphs? How can we go through this process of starting with unstructured data that has a lot of connections in it to producing more structure that we can leverage for data science problems? And so that leads us to a library. It's called KGLab. We started on this, we've been working on a lot of these things for a long time, but as an official project, it got started last October, and it's really picked up. It's an abstraction layer in Python, and here's links to the repo and forums and all that. The idea is that in the graph space, there's a lot of really interesting open source. Unfortunately, they're broken out into different camps, and they don't really talk with each other. The people doing W3C technologies in RDF-lib, they do great things, but they don't really have an integration path if you want to use NetworkX to do graph algorithms. And neither of them have an integration path if you want to go out and use PyViz to do some nice visualization. And if you happen to have some sort of probabilistic graph problem and you're doing, statistical relational learning, and you're using something like PSL or PGMPy, nobody talks with them. So the problem was, how can we establish common ground, abstraction layers to integrate open source projects? And while we're at it, let's make a lot of paths out to things that we know, like pandas, NumPy, scikit-learn, PyTorch, etc. And while we're at it, let's do the right thing and make this stuff so we can parallelize it using Spark and Ray and Arrow and Rapids, on and on and on. That's the gist of what we're doing with KGLab. And there's a very ambitious roadmap, although we've knocked a lot of this down. We have a lot of these integrations now. Also, there's a related project I've been working on for a number of years, going back to 2008. I've been working on TextRank. PyTextRank has become rather popular in the Python space for doing relatively lightweight but very effective entity extraction from text. And also, you can do some summarization. Very closely related, the two projects work together. So let me go into the last parts of this rather quickly. KGLab, we do a lot of things here, but I'll give you a little bit of a flavor. If you're ever working with semantic graphs and the whole W3C space, like RDF, we do that. And we try to make it as simple and painless as possible. If you've ever worked with RDF-lib before, it takes a lot of coding. So we try to provide an abstraction layer to make this simpler. And we also have a lot of different serialization formats supported, but importantly, we support JSON-LD. A lot of people talk to that. More importantly, these days, we're using Parquet, and it's orders of magnitude more efficient than any of those others. It also integrates well with Spark and with Trino and Cassandra and other things. Works really well with GPUs. There's a number of paths for working with Cairo, and Matplotlib, and PyViz, and exports to Gephi, and things like that for doing visualizations. Again, really just a few lines of code. If you need to query, you can use Sparkle. This is built in, and we bring the results back as, well, you can get them as an iterator of rows, or you can get them back as a pandas data frame. If you need to do some sort of validation, one of my favorite projects lately is called Shackle. It provides shape constraints. You can apply rules to validate a graph, like building unit tests. Also, really great part of this. And when you need to jump in and do graph algorithms, we have transforms there and back for working with NetworkX, iGraph, and some others on the horizon. So the reason is this. You can use graphs for a lot of things. They really fit complex data problems. when you look at the space of what's being implemented for graphs, it's kind of all over the map. And I've tried to represent this here. Some of the solutions work really well with uncertainty. Some of them are much more formalized. They're much more of an analytic solution. And so, axiomatic transforms in SCAs don't really fit well with graph embedding in PyTorch. We're trying to bridge that so that you can build applications that mix and match between these different parts and leverage these different technologies. And so, for instance, here's an idea of using probabilistic graphs with PSL, which I find extremely useful for uncertainty. Also, graph embeddings using something like PyTorch Geometric. So, real brief, in the time remaining, I want to show a general pattern for what we're doing here, along with an example. So, if you think of an idealized machine learning workflow, this is the kind of thing you're typically working with: data prep, feature engineering, training models, etc. Let's look at an example of that. Here's a data set from Kaggle, and it's from food.com. It has 250,000 recipes, all their ingredients. We take it as a CVS file and build it into a knowledge graph. So you've got to have some data prep. You've got to go and do some deduplication in addition to reading CSVs. But you've got to be able to infer relations out of what's there, somewhat connected, but it could be connected more. You probably want to have some feedback loops as far as getting people in there to understand how to label things appropriately, apply annotations using rubrics or Snorkel, something like that. And then you want to go out and build a graph and then start to measure some of the data quality within it. RDF and Shackle are really good at these points. Then you can go out and run some graph algorithms. Perhaps you want to analyze the structure and find out what's the most popular ingredient in this set of recipes for how to make my favorite food, char siu bao. Maybe you could use Leiden or K-cores or some sort of centrality measure for that. On and on and on. You can apply for the different parts of the use cases, these different types of tools, all within the same structure. And again, we're not trying to invent a lot of new code here. We're really trying to do integration and test and tutorial added on top of other existing open source libraries. So all of this is online, and there's about 12 different Jupyter notebooks on our docs page that go through this step by step and use this worked example with the food.com recipe data. So you can take a look and run those. We have Docker Compose that we're building out of GitHub if you want to run it in Docker. And there's some other tangential tutorials. I really love what's going on, my friends in Spain, in Madrid and Valencia. There's a company called Recogni. They do something called Rubrics. We're very close friends and work together on our projects back and forth. Also, I want to give a shout out to our GitHub sponsors on the projects and also to the knowledge architecture team at BASF Global Digital Services. They've been hugely supportive, Jürgen Müller and others there. And we'll be going into this in more detail at some tutorials and keynotes and whatnot, other conferences coming up over the next several months. And then with that, I would like to say thank you very much. I appreciate it. We have a lot more details online. I wanted to save some time so that we could have some questions here. I have only one screen where I'm at, so I'm going to leave it on this page right here, and we can go to questions.
Thank you, Paco. That has been a great talk, and I particularly appreciate the shout out to my friends in Madrid and Valencia, who I don't know yet, but now I will. There are questions from the audience, and here they come. The first one is, does the KGLab abstraction layer work with Neo4j, and how is it different from NetworkX? I'm meshing them both.
Yeah, no, that's a great question. So, Neo4j, if you haven't worked with it, Neo is arguably the most popular amongst the graph databases. And it really started out as like a single instance. They've tried to go into more distributed areas, but it's not going to be the thing you use for really, really large graphs as much. But they have a long tail distribution of customer use cases. So very, very popular. It is a database, and you can do queries inside of it. Although some of the other things you would want to do with graphs aren't going to be quite as native inside Neo4j. There are integration paths. We do have a connector. There's something called Neo4j. Well, actually, there's a few different ways, but there's a way of bridging between Neo4j and semantic graphs, and so we can use that to import. And in fact, one of the developers just used it for, I think it was a 40 terabyte project. It was huge. It was enormous. So we've got a good industrial strength integration put in place there. The thing that it differs from NetworkX, NetworkX is a Python library for algorithms. It doesn't have anything to do with persistence or really any other parts of graph other than let's get a lot of different algorithms implemented. This is something that Neo4j is not really what you want to be using. Very separate kinds of use cases. So for instance, if you wanted to run PageRank or betweenness centrality or perhaps some sort of connected components, Neo4j is NetworkX is brilliant for that. So we integrate with both of those.
I see. And someone asked, thinking about the idea of sensing emergent patterns from unknown unknowns, what strategies can experts use to separate what they see as an emergent pattern that they sense from relevant experience that they have and from implicit bias they may not be aware of?
Certainly, very good question. The experts do. This is one of the things we find over and over again. If you take somebody who's an expert in global supply chain and logistics, and you put a graph of their data up in front of them, they start to see the connections. Especially if there's any kind of a real-time update aspect, they get it right away. I mean, this is how they think. So, typically in a domain, the experts will have these kinds of insights. How can we make it easier for them to surface? So if you have a 5 billion entity graph, they probably won't catch all those patterns. You probably won't be able to visualize them all on one screen. So what can we use to basically shine a lens? And this is where the algorithms come in handy. Some of the query preprocessing, certainly a lot of work that's going on with deep learning is basically shining a lens in different parts of the graph that might be very interesting given the kinds of things that that expert is looking for. And this is where the graph data science comes in very handy to work with the domain experts. But the second part of the question is, what if it's something they're missing? And again, this is where by having automation, having very large deep learning models go in, learn those patterns, then you can say, well, the expert, actually, I'll point out a great use case of this. Novartis has exactly this problem. They take all of the research coming in terms of pharma, and they run it through a graph, and then they build models out of that to predict the interactions between different genes, different molecules, and different diseases. And what they found the first time they did it, they presented it to their biologists. The biologists said, oh, we know all this stuff. Well, we know 80% of it. So the company said, well, what about the 20% that you didn't know? And they said, hold my beer. I'm going to go back to the lab. And then they found out actually very important discoveries by that 20% they hadn't tried before. And so now this approach, leveraging graph analytics, has become part and parcel of the research strategy at Novartis and at other kinds of pharma. So this is where, there may be some bias on the part of the domain experts. How can we use AI technologies to augment that? And in particular, we have one project at KG Lab where we're using reinforcement learning to surface a leaderboard of emergent patterns that maybe nobody bothered to check before.
Thank you. You've mentioned working at bigger scale of data, and it segues into the next question from an audience member who asks, how does KG Lab perform at scale when compared with libraries such iGraph or NetworkX on algorithms like betweenness centrality? So the idea is now performance, where you mostly focus on capability before.
Very good, very good. Well, I mean, things like running betweenness centrality on NetworkX or iGraph. What you probably want to do, there's a few slides back, there was an illustration of this. Have your graph, manage your graph. You can use different technologies to manage it and persist it. When you get to the point of needing to use some of these algorithms, you typically want to take a projection off that. You want to take a subgraph. And in fact, when you're working with NetworkX, you must. So that's one of the abstractions that we have, is how to project out part of the graph as a subgraph. You won't be using the entire graph when you run it through the algorithm. And in some ways, there are actually some pretty good algorithms to try to filter and pare down. I did a multi-scale backbone, for instance, that's in production use in Hungary. I just found out about that at one of the recent conferences. There are techniques of being able to scale down, pare down, if you will, a subgraph to get, again, the lens on the part that you need. As far as how does KG Lab scale, it really depends on what kind of infrastructure you have. I guess without letting the cat out of the bag, I do other work besides KG Lab, some of which is currently private in early stages, but maybe someday soon will be open source. That's in active negotiation right now. And it's something that's built using much the same technologies we use with KG Lab. using Ray for scaling on a large cluster. And to be clear, we're already at pretty high scale. We're aiming for trillion node graphs by the end of the year.
Thank you. That's all the time we have, unfortunately, but thank you so much for giving
Thank you,
us your
Javier.
time today at PyCon AU, and big hand of applause. It's going to be virtual and venue-less, but thank you, Paco.
Much appreciated. Thank you, Javier. Have a great day.